About the MCAT, since we were talking about the MCAT, in my YouTube channel, I have two playlists. One go over optics, okay, geometrical optics, because it's in the MCAT. Not only that, people who want to go into optics, okay, that might help you, because we don't have time to go into much details. And then there is another playlist where I go over fluid. So very important if you are going into the medical field, because there is a fluid system inside us in addition to the electrical system and the mechanical system. Okay, so it's in my YouTube channel. I'm not monetized, okay? I'm not going to go very far with 100 or 200 subscribers. And mostly students that they forget to unsubscribe. But there is another playlist also going through oscillations. So that's just for you. And someone just told me that for the MCAT, it's more conceptual questions on based on medical applications, right? So anyway, physics is very simple. First, you understand the concept, and everything else is just algebra. So you have to be very strong with algebra, and then you need to understand the concept, and then you will be fine. Algebra is really what you need, not even calculus. Algebra is really the foundation. Okay, so let's keep going. You have an assignment, I think, maybe for this week. Okay, and there's a pop quiz today. So definitively a question on the pop quiz, not on the pop quiz, but on the final. Remember, very educated beaver. So very is the direction of propagation of the electromagnetic wave. Educated is the electric field, and beaver is the magnetic field. Do you see? Okay. So the source for an electromagnetic wave, it's going to be oscillating charge, okay, that will induce an electric field, that will induce magnetic field, that will induce an electric field, that will induce magnetic field, and so forth and so on. So an electromagnetic wave has two components, an oscillating electric field, an oscillating magnetic field, and they induce each other and they are in phase. So we already talked about that. If I try to trick you and I try to tell you that, oh, gamma rays, they have more energy to burp out, so they're going to move faster. No, all here go at the same speed, the speed of light. But if the wavelength is going to be very small, then the frequency is going to be very large. They are inversely proportional, and the energy of the wave, okay, is proportional to the frequency. So larger frequency, larger energy. Those here, okay, you can think of them as they behave more like bullets when they interact with matter, right? So for example, UV, for example, if we didn't have the faculty to tan, for example, then UV can get into our skin, and because it's so small, it can knock out electrons, damage DNA. Luckily, our DNA has evolved in such a way that it can repair itself or commit suicide. So anyway, those are not very friendly waves, and those are friendly waves. You see that the visible light range here is very small. So most of the waves are invisible. So talking about the medical field, okay, so now we're going to talk about um, electromagnetic waves applications. Okay, so most of my slides here, okay, comes, it's not the slides, but everything I'm going to tell you, some of the things I'm going to tell you, okay, it's from that book here. It's a very, very nice book, very easy to read. There is no algebra. I mean, just arithmetic times to time, but not that much. And it's called Physics for Future Presidents. Or you have another version, and it's called Physics Behind the Headlines. So if you go to the medical field, it's very interesting to read. Okay, Physics for Future President or Physics Behind the Headlines. So it's $6. You can rent the book. Okay, very interesting. Okay, So let's start from gamma rays going to radio waves, and I'm going to try to focus on the medical field. So gamma rays, okay, they are the smallest, okay, of all. So very, very small wavelength. The size is about the nucleus. So because the size is the nucleus, you produce gamma rays during nuclear reaction. So for example, in an atomic bomb, okay, the idea is it's gonna be that you use a neutron as a projectile, okay, and you force uranium to split apart, and you're gonna have gamma rays being burnt out into the process. Okay, in a PET scan, that's what we're going to talk about, but we already talked about that if you have an anti-electron and electron, okay, so it's matter, antimatter, when they meet together, when they meet each other, they're going to destroy each other, annihilate. Okay, so matter, antimatter will annihilate each other, and matter disappear, so the mass disappear, and it will give you a burst of energy in the form of gamma rays. Okay, so how does a PET scan works? Okay, so for example, let's say, God forbid, you want to know what's going on in the head to see if there is a tumor, if the tumor is cancer or not cancer. So you will give the patient radioisotope, okay, so that you mix with sugar, for example, because cancer cells love sugar. So radioisotope will be, for example, oxygen, radioactive oxygen, because oxygen goes to your brain, so the brain consumes a lot of oxygen. So that radioisotope will go to the brain. Inside your brain, it will decay, okay, and it will give positron. And positron is what? Positron is an anti-electron. So when the positron it's going to meet electrons inside the head or inside the tumor, they will annihilate each other. They will destroy each other, and it's going to burp out gamma rays from inside out. Okay, so you're going to have bursts of gamma rays from inside out, from inside out, from inside out. It's always in one direction and the other direction because of conservation of momentum. So what are you doing here? You are highlighting the inside of your brain, of your head, okay, using gamma rays. Why do you want to use gamma rays? Because gamma rays have such a small wavelength that you're going to get a very good resolution. So you can see all the details. Okay, because everything is limited by the size of the wavelength. You cannot see anything smaller than the wavelength you are using. So if you are using an optical microscope, okay, so visible light is about 600 nanometer. You cannot see anything smaller than that. So you cannot see viruses, for example. If you want to see viruses, you have to use electron waves. So electron microscope. Is that clear? So that's how a PET scan works. It works because a radioisotope that you give to the patient, okay, it's going to decay, give a positron. Positron will combine with our electron, and you're going to be highlighted from inside out. So that's a PET scan. So if you go to the nuclear medical field, nuclear medicine, I think they have a lot of opening. I'm not sure. I will think so. So you use that for detecting cancer, for many things. There has many applications. So the idea is that you need to use radioisotope. So it means isotope that will break very quickly. So it has a very small short life. So it means if you have carbon 11, so it's radioactive, after 20 minutes, half of it is gone. Okay, so carbon 11 will be used for that kind of tumor. I don't know. Oxygen will be for the brain. Iodine will be for the thyroid, and so forth and so on. So how do we make those radioisotopes? It's made in hospitals. Okay, so that's why it's expensive. Okay, so insurance sometimes they don't want to cover. PET scan, you have to do a lot of paperwork. You don't want to have PET scan too often, okay, because you are exposed to gamma rays. So it's always a balance between risk and benefit. Any medical procedure that you have to go for, risk, benefit. So anyway, how do you make that? You use a cyclotron. Remember that? So if I try to trick you, a magnetic field will bend a proton or a charged particle, an electric field will accelerate it. Okay, so with a cyclotron, you can take a proton, for example, accelerate, bend, accelerate, bend, accelerate, bend. You use your proton as a little projectile, so you can hit, for example, a nitrogen molecule which is not radioactive, and it will turn into something else, radioactive carbon. So actually you are playing alchemist, okay? It's like alchemistry that you are doing. So then the carbon 11 is mixed with sugar. Sugar goes to the cancer. And then you see here, it's going to emit, it's going to decay, giving you a positron that combine with electron and pyung, pyung, pyung. You are highlighted, okay? So for those who want to go into that field here, you can read over and learn about it. Okay, I had a student who was like 2 years ago. She was taking this class and she told me she was working in a hospital, and that's what they did. They did the PET scan of the thyroid here. So if you work in a hospital, you need to be very good at handling those radioisotopes. Okay, so I used to teach nuclear medicine students. Okay, so PET scans are expensive and they require the hospital to have those cyclotrons to make radioisotopes with a very short life. Alternative is what we call SPECT scan. Okay, so in that case, the gamma rays don't go through you. Okay, so you don't have such a nice 3D image, but it's gonna bounce off. Like ultrasound, when you are doing an ultrasound, you are using sound waves, okay, to highlight the inside, except the sound waves will bounce off. So same thing here. So this is called a SPECT scan. And as usual, you can dig a little bit more if you want. I'm just giving you like a I'm just skimming through space. Okay, lots of gamma rays happening in space. You have what is called gamma ray burst. So, for example, if you have two neutron stars orbiting each other, when they're going to merge together, they can give you a black hole, for example. Okay, so when that happens, it's so violent that you have a burst of energy. That will be gamma ray burst. Or it can happen also if you have a huge star at the end of its life. Okay, it's gonna collapse. Gravity tries to win. Bada boom! You have a supernova. Okay, and you have bursts of gamma rays. So we almost went to World War III in the 50s during the Cold War, because scientists and military were seeing bursts of gamma rays all over in space, from space. So they thought that maybe the Soviet Union were testing nuclear bombs, hydrogen bomb, and so they were ready to push the red button, and then they realized, no, it's something happening in space, right? So it happens when you have a merger between black hole neutron star, or a merger between two neutron stars, or a star collapsing. Another possibility, you see, you can have an electron moving, it has kinetic energy, and it's going to bump into a photon with low energy. And so the energy of the electron will be transferred to the photon. Okay, so remember, a photon does not have any mass, but the energy will go in the form of radiation. Okay, so instead of being a red photon, all of a sudden it's being promoted to be a gamma ray photon or an X-ray photon. So when you increase the energy of a photon, okay, you're going to change its wavelength. You're going to change its frequency. You cannot change its speed. Okay, remember, if I try to trick you, all photons, they all go at the same speed in vacuum. Okay, when it's going through glass, it's going to slow down. But there is no difference between a red photon, a gamma ray, X-ray in space, in a vacuum. They all go at the same speed. It's not the same when they go through glass. When they go through a prism, okay, blue does not have the same speed as red, so it depends on the wavelength. But in space, they all go at the same speed. Okay, so let's talk about X-rays. Okay, so like gamma rays, it's very ionizing. Okay, so it's very damaging. It's also penetrating, so it means it can go through you. Okay, the only thing that can stop them, not totally, but partially, is the bones. Okay, because bones are made of calcium. Calcium are big enough to stop the X-ray. So that's why you will see a shadow. So let's review. It's a nice review. Here you have a high voltage. So the electric field always goes from the, what it's called, the anode, positive. Here, this is positive terminal, and to the cathode. But the electron wants to go against the electric field. Okay, so because there is an electric field, the electrons will speed up. So remember, for the final, I forgot if there is a question on that or not, but it has potential energy here. This is minus and this is plus. Potential energy equals Q times V. V is the voltage, okay, or EV. Q is the charge of an electron. V is your voltage applied. So the electron, okay, has potential energy, QV, and all this QV will turn into kinetic energy, 1/2 mv squared. Yeah, I think there is a question like this. Okay, so all that electrical energy turn into kinetic energy for the electron, and here they're going to crash into a heavy metal target, and all that kinetic energy is going to turn into X-rays. By changing the voltage here, you can change what type of X-ray do you want, right? Is it for the dentist, or is it for the bones or experiments? So you can have soft X-ray, hard X-ray, depending on the voltage. Okay, any question? So this is interesting. That comes from your book, not the book I mentioned before. But anyway, X-rays were discovered in 1895. Okay, just by chance. He was Röntgen. He was experimenting with a vacuum tube here, like this one, right? And at the end here, he realized, like, he put, I think it happened by chance, but here you see the hands of his wife, and you see the ring here. Okay, so I guess he didn't want to use himself as a guinea pig, so he used his wife. I think it's wise. And he said, it's a very famous quote, he said, "Have seen my own death," because it was the very first time you could see the skeleton of someone alive. So that was the very first time. Okay, he called them, this radiation was called X-ray because they didn't know what it was. So it was X-ray. Okay, same thing with alpha, beta, or gamma rays. Okay, at the time, they didn't know what they were. Okay, didn't know that they were photons from electromagnetic spectrum, so they call them alpha, beta, gamma. So X-rays, right? So as usual, you know, each time there is a discovery done, okay, a new technology that is discovered, all of a sudden, you know, people want to ride on that new wave to make money. Okay? They turned that into a way to make money. So at the time, they didn't know how dangerous X-rays were. I mean, a little bit is fine, but there is a way, there is an equation. You can find how much damage you can do with X-rays. So of course, you want to do X-rays at the dentist because you can die from a infection, but not too much. So at the time they started to advertise for using X-rays to cure headache, okay, and not controlling the amount of radiation that was given to patients. So maybe not the best idea. Okay, this is also not a good idea that was in the news. So it's between Morocco and Spain. Okay, so you just have a border between Morocco and Spain. So people try to sneak inside Spain because then they are in the European Union and then they can go wherever they want. So they had a very bad idea to put a kit in the suitcase. And of course, X-rays exposure could be very bad. So don't do that. The X-ray, the amount of X-ray for suitcases should not be the same as for people. Of course, okay, another bad idea in the 1950. Okay, so each time again there is a new technology, follow the money. So that was also a very bad idea, but doctors at the time, experts told you, oh no, it's safe, don't worry about it. So in the shoe stores, and that comes from that book, okay, Physics Behind the Headlines. In the shoe stores, okay, that was very fun for the kids. There were these X-ray machines. So you go to Peles, I don't know, shoe store, okay, you will put your uh, feet into here, okay, and you could see your bones. So imagine the kid, that was so fun to do that, right? You can wiggle your toes and you could see your bones. So they use that to say, okay, these shoes, they have, they are not fitting you well, you should get those shoes. And they were used a lot. But that's bad because when it comes to cancer, it's all about probability. Some people will get it by using those machines, and some people will not get it. So they came up with something called the linear hypothesis. So the linear hypothesis is a way to find the probability to get cancer if you are exposed to that much radiation. So they came up also with another unit for radiation, which is called the REM. So the REM is a way to find how much damage is done to the cells, biological cells inside the body. So this is called the REM. So the linear hypothesis says that if you have one REM, if you are exposed to one REM, your chance to get cancer is 1 out of 2,500. Okay? Or if you have 2,500 people getting each one REM, that means one person will get cancer. Okay? So those machines will expose people to 30 REM. Okay, so your chance to get cancer is multiplied by 30. Will you get cancer? It's probability, okay? When you get to the body at a very small scale, everything is probability, okay? So it means if you have 30 REM, okay, so you have 30 times the chance to get cancer. So if you have 2,500 people putting their feet inside that machine, 30 will get cancer. Is that clear? So, for example, we can say if you have 100,000 people using that machine, so you put 100,000 here, you put an X here, so 1,200 will get cancer. So 30 out of 2,400, 2,500 is a small percentage, but of course you don't want to be among those 1,200 people. So very, very, very bad idea, okay? This is called the linear hypothesis, okay? So it's a way to find the probability to get cancer given a amount of radiation someone is exposed to. So interestingly, that linear hypothesis doesn't work below 1 rem. So, for example, interestingly, if you go to Colorado, there is a lot of radiation from the ground, okay, because it's a lot of uranium over there, but you don't have a higher percentage of people dying from cancer relative to another state in the US. So it means below 1 rem about, it doesn't work. Above, yes, it works, right? Okay, so another application, it's a CAT scan. You know, I guess they love animals. You have the PET scan, the CAT scan. So CAT scan also uses X-ray, okay? But it's what you're gonna get is a tomography. So it means you have X-ray going through here, X-ray in this direction, X-ray in that direction, okay? So then you have sensors all around, and using the magic of computers, you can get an image. So CAT scan, more resolution than MRI, less resolution than PET scan. So smaller is the wavelength, more resolution you get. CAT scan. Okay, so that I found in the news like a couple years ago when I was teaching that nuclear medicine class. So I wanted to find fun stuff to share. They found in a Buddha. Okay, so they put a Buddha in a CAT scan. Okay, and inside there was a skeleton. So someone told me about it. It's I don't know. I think it's somewhere in Himalayas or the monk. Okay, so you have some monks. I don't think it's done anymore, of course, but used to be that monks they will starve to death. Okay, doing meditation or something like this, and they will drink special mushroom to really clean themselves, right? And then you know they enter meditation and they die, and then they will shove their body inside inside the Buddha. Okay, so that was a way for them to enter heaven, you know, clean and uh, and while doing meditation. So I thought it was an interesting story. They did not want to crack it open. Okay, so they had to do a CAT scan and you see what is inside. Isn't that interesting? Okay, so don't drink too much mushroom, I guess, because otherwise it's really for cleaning. Okay, so that's from the book. Okay, you have a different way to do it, and it used to be used in some airports, and this is called back X-ray. So again, in that case, it's like ultrasound. So X-rays will bounce off. Okay, that's also a different technology for imaging. And the way it works is that photons, like X-ray photons, they can bounce off electrons because the size of an X-ray photon is smaller than an electron. So this comes from the book I was telling you about. It's called Physics Behind the Headline, and they used. I don't think they do it anymore, but they used to have X-ray backscatter, so it's using X-ray to see what is inside trucks. So of course you can imagine there is a lot of controversial here because is it ethical or not? Because people are not aware that they are being that they are bouncing off X-rays uh, of them, and they used to do that when you used to go to China. I don't know if they do it, still do it. They will use back X-ray to see if you are wearing a gun or not. So they used to do that at airports as well, but it's not done. In the US, they stop X-rays because it was too revealing. So I guess the agents, you know, they were focused on something else versus security. So they use a different technology. So they don't use X-ray. So it's not revealing anymore. So don't worry. Okay, so gamma rays, X-rays, UV. Okay, so UV still have a very small wavelength, and it can be used to destroy bacteria in water. Remember during COVID, there was people very smart who were selling those UV lamp, and everyone was like this with the phone and the computer. That was very smart to sell that. Okay, you could make money like this. So anyway, he's very famous. He's a professor at University of Berkeley, and he found a way to purify water for developing country, especially for example in Africa. So they don't have access to clean water. So it's very cheap to have those UV lamp, okay, shining over a bucket of water that they will get, I don't know, from the river, for example. And this UV radiation will kill all the bugs inside. So it was a very cheap way, simple way to purify the water. And it's also used if you go for a manicure or whatever, they use UV light. It's also used in surgery. Surgery, they put the instruments under UV light to kill all the bugs and the bacteria. Okay? That's a good question. It's again about probability. So it's not like X-ray and gamma rays, but okay. So it's a good question. You have different types of UV. You have UVC. So UVC will be stopped by our atmosphere. Then you have UVB, and then you have UVA. The dangerous part is UVB. So that UVB here has enough energy that it can destroy DNA. But in most cases, we have evolved in such a way to fix DNA. But yes, it can cause skin cancer. But I refuse to have like a sunscreen, because if you look at sunscreen, it's also like suspicious. So anyway, I rely on time, as you can see. But yes, the answer is yes. It's a probability thing. Okay, so I think he did that in 1993, and he also worked on efficient stove. So that's another story. Especially there was a genocide in Sudan, Darfur. In Darfur, okay, there was a genocide, and people were very very much struggling. So he helped them to build very efficient stove with less smoke. So he's also famous for that. Okay, you can Google him if you want. So UV light can be used to destroy bug. Okay, so it's efficient for camping, for example. In a fluorescent lamp, okay, it's used also UV light. So the way it works, okay, you apply a voltage, the electrons are gonna speed up, okay, but inside you have mercury, okay. So that's why you cannot, usually you have to recycle the fluorescent light bulb, because inside they have mercury, and here you have a special phosphor coating. You see that white here is phosphor. So the way it works, those electrons, they accelerate, okay, they're gonna excite the electrons, okay, so they're gonna burn out the energy and excite those electrons from mercury. Those electrons on the electron shells, they will go to a higher level of energy. So the electrons from mercury will get excited, okay, they get high, and when they relax, they're gonna burn out uh, visible light. UV, okay, will be high energy photon. The UV will be protons from UV will be absorbed by phosphor, and phosphor will re-emit visible light. Higher energy banana, when electrons go back to a lower level of energy, they emit photon, UV photon. Okay, so the UV photons are emitted by the mercury electrons, and then the UV photons are absorbed by the phosphor that will emit visible light. Okay, so for example, that's for you if you are in biology. It's not very well explained, at least at the time when I read the paper. So maybe they changed now. But you have some species of scorpion during the day, they're gonna absorb the UV from the sun, and at night they will emit visible light. So they go visible during the night, like they are fluorescent. Okay, so UV is absorbed, those UV will be emitted as visible light. It happens also for minerals, right? If you go to a science museum, those minerals here can absorb UV from the sun. So here they are under UV light, and they will re-emit visible light photons. So absorb UV photons, re-emit visible light photons. In between, some energy has been lost, maybe to heat. Is that clear? Okay, so you can do that with Crayola. The Crayola, they are fluorescent. So if you have a Crayola pen, go under the sun during in the dark, they will shine because they absorb UV and emit visible light. Isn't that interesting? Okay, so what happened there? That I'm sure you all know that I think in 1990s they stopped using this chemical called it's a group of chemicals called CFC. So it's chlorine fluorocarbons. Okay, so you have different kinds of them, and they were used for fridge. For example, inside the fridge, for example, you had something called freon. Freon is a type of CFC, it's a gas. So it was very convenient to have a fridge working, or it was used in aerosol spray or solvent. Okay, and the issue with that is that it was destroying the ozone layer, and the ozone layer is what protects us against UVB from the sun. Okay, you don't want UVB. That's what causes cancer. Okay, so I don't know, you are in chemistry, so I'm sure you can understand what's going on. Ozone is O3. Okay, so O3 react with UV, okay, to stop it. It will absorb UV. So that's a good thing. But CFC, it's there forever. It's like a forever chemicals. Okay, it stay in the ozone layer forever, and it is destroying it, and it doesn't go away. Yeah, I'm sure you learned that in chemistry, right? CFC, right? Did you learn that in chemistry? No? No? In 1987, there was an agreement among all the countries in the world to stop using these chemicals here. They were used in all the spray. Okay, so when I was younger, long time ago, the sprays that we were using, and they all use CFC, and the fridge also. So they stopped using it because they realized that it was damaging to the ozone layer, and ozone layer is what protects us from the UVB. Is that clear? Okay, you can, because you are in chemistry, okay? Heavy load of chemistry class, you can see how it works. So especially above the Antarctica, you could see that the ozone layer was destroyed. It's not totally understood why there and not in other places. So for example, if you go to Chile, they tell you have to put sunscreen. Okay, the UV is too strong because the ozone layer has been damaged there. So I think there is a law in Chile where they force people working outside, that really to wear sunscreen and hat and everything to protect themselves because UV radiation is stronger than here. Okay, so you see you have what we call near UV. Okay, it has a larger wavelength. UVC, most of it, I think all of them will be stopped by the atmosphere, and UVB, that's the bad guy. Okay, and it doesn't have the same penetration. Okay, is that clear? Okay, so then you have the visible light. So it's a very small range of the electromagnetic spectrum. So that means our eyes are very poor sensors, right? They can only detect visible light. The small wavelength will be for blue, about 400 nano. Nano means 10 to the negative 9. Large red wavelength here. Large wavelength will be for the red. Is that clear? We need red, by the way. You know, that's why they have like red therapy, red light therapy. Okay, so interestingly, blue will bend more than red. That's how you get a rainbow. Okay, it has to do with the speed of light being smaller for blue than for red in glass. Mm. Right. Okay, another application here is fiber optics. So there is a principle that if you want to carry information like bits, okay, so Wi-Fi or I don't know, audio signal or video signal, okay, so it's digital 01100110001. So each bit could be a 1 or a 0. The number of bits per second that you can transport depends on the frequency of the wave you are using. So if instead of using radio waves, you are using visible light, then you can transport more data. But it's more expensive, of course. That's why you are using fiber optics. Okay, so you can mine for bitcoins more efficiently if you are using fiber optics because there is more bits traveling per second. Okay, is that clear? Yes, okay. So then infrared, okay? You're not spacing out? Conceptual questions, you never know. For MCAT or whatever, infrared. So infrared are actually heat wave. Okay, so when you go outside and you feel the warmth from the sun, that's infrared. Okay, so the one who discovered infrared, his name was William Herschel. And he had, I guess, a very curious mind. So what he did, he took a prism. So that experiment was already done by Newton before. And you have the rainbow here, you have all the colors. And he got the idea to take a thermometer to see if there was a difference between, for example, yellow, blue, or red. And then he put his thermometer past red. And all of a sudden, boom, the thermometer was reading larger temperature. So it means you had an invisible wave here just after red, and that was infrared heat wave. So you can do that on your own. Okay, you can have a box here, you have a prism, you have to orient the box the right way. You have your rainbow. You take a thermometer here, you bring it close to the red, not quite the red, just after the red, and you see the thermometer increase. Isn't that interesting? Okay. William Herschel was an astronomer, and what about him? He was British. He was British, and he was the first one to build a huge reflective telescope. Okay, and his patron was the King of England. And why do I tell you that? Because he discovered Uranus. Okay, so he's the one who discovered Uranus, and he named the planet after his king, George. So Uranus used to be called George Star. Okay, huh? Isn't that interesting? And then they decided that it was not appropriate to call the star after just the King of England, you know. So anyway, applications in the medical field. So each time you have a wave, you can always use it, okay, to scan, okay, to go through the body. Either you have the wave bouncing off, or you have the wave going through, okay, but you can highlight the inside. So you can use near infrared, so it's called near infrared spectroscopy, to scan, okay, to highlight the outside of the brain. Okay, so go for it, look it up. I don't know in which case you want to do that. I'm not sure of the applications of that, but that's the idea. Okay, so you have a source of near infrared. It will go through your outside brain and it will highlight what's going on. So you need to use detector and then a computer. So this is called near infrared spectroscopy. Okay, another application. So infrared are heat waves. Okay, they are the size of molecules. Okay, so when molecules start to move very fast, they're gonna emit infrared. So you can use that to detect infection, or God forbid, a breast cancer. So for example, here you see this area, and of course it has to be colorized using a computer. Here you can see the tumor, and it's a very cheap way to investigate, because all you have to do, you put a special coating, a paint on it, and you see that here it will radiate more infrared, because there is a cancer. That means temperature will be higher. Can be used also to spot an infection. You see, infection, temperature will be higher, so you can spot it. Okay, so because there is a law in physics that says that radiation, the type of radiation that you have depends on the temperature. As you increase the temperature, you go from uh, near infrared to far infrared. So you're gonna decrease the wavelength, increase the energy. So the type of radiation that you get depends on the temperature. So if I look at you in the dark, okay, you're gonna all shine infrared, because thank God you are alive, but you are gonna shine one type of infrared. So I will know exactly who is sick and who is not sick, right? I can exactly tell the temperature of the human body just by looking at the infrared you are emitting. So the type of radiation will give you the temperature. So the radiation from the sun, it's kind of white. Okay, so I can tell that the temperature of the sun is about 5,000 Kelvin. Okay, yes.
Based on the graph, the section that has like the dark blue violet portion, would that it means that it's not as hot as the infrared?
Very good.
That is
No, it means it's less hot. You are right. So they are using differential. So it's still, it means it's a normal temperature of the human body, for example. But here, that means is hot. So that means here you have an infection or a tumor. So here, of course, it's going to be hotter here, and some spots will be cooler.
why is cancer specifically hotter than
Because it keep consume sugar. So the temperature will be larger. It's like an inflammation going on steroid. So you have an increased temperature. By the way, about cancer, if you're interested, and God protect us, it's very scary. I lost people. So there is this professor, very famous professor. His name is Thomas Seyfried. Okay, he he works at the Boston College, and he's doing a lot of research on cancer. He's very interesting. He has YouTube video, okay, because he gave lectures, but he has two books. One book is easy to read. That's the one I read. And one book is very hard to read. It's like a textbook. So maybe you want to read the textbook one. But he explains that cancer is a metabolic disease. So it means it's usually the cells, they use oxygen and they can use sugar, but they use oxygen. Whereas a cancer cell is like fermenting. Okay, it's like when you make a dough and you want the dough to you have to add yeast. Yeast is a bacteria and it doesn't like oxygen, right? Cancer also. So cancer has a different way to multiply itself. It's using sugar and no oxygen. Okay, so he explained that, and he says that one thing people should do is stop eating sugar when, if God forbid, they have cancer, because you stop feeling it. It had also different way because it can be very cunning, so it has different way to survive. But he explained all that if you are interested. If I knew what I know before, I could have saved someone. So anyway, that was a parenthesis. Okay, here another application. You can look at a house with those special infrared sensors, and you can spot where the heat is leaking out. Okay, so maybe there is an issue with the roof. So maybe you can fix the roof. Or you see here, of course, the heat is going through the windows the most. Okay, you can look at someone here. You see that here it's going to be cool because he's wearing sunglasses and different part of the body. The head, of course, the head is where you are losing the most heat. That's why you have to wear a hat, but not here. But if you go to some place cold, you have to wear a hat because that's where you have all the blood vessels, blood. Yes, thank you. Any question? So that's something interesting. Turns out that visible light will be stopped by dust and smoke. Okay, visible light has such a small wavelength, okay, that it will be stopped by smoke. So if you want to save someone who is inside the smoke, you won't see that person just using your eyes. But if the firefighter, they can use infrared sensors and then they can see the people. Because infrared, okay, they have a longer wavelength, and when they have a longer wavelength, okay, they don't care about the dust. They're going to bend around the dust. Okay, that's called diffraction. So if the wavelength is long enough, very long wavelength, and you have a dust particle here, it will bend around. So infrared, okay, does not care about the dust and the smoke. It will bend around. So you can use infrared sensors to see people inside. You can save them. If you are using just your eyes, you won't see them. Okay, it's all dusty and smoky. So that's a nice application. So I found that, I don't know if you remember that episode, I was a fan of Family Guy. And one of the episode, it was about the Predator. So I think it's a movie from, huh? Well, was it with Stallone, the Predator? No? Yeah, they were alien attacking people. But is that Arnold or Arnold? Arnold? So the story of those aliens, you are right. They were aliens, like very weird looking aliens, and they didn't see, like some animals, they don't see visible light. Okay, they have different waves, a different way to find to see. You don't have to use visible light to see, like bats. Bats, for example, they use radio waves. Okay, they don't use visible light. So these aliens use infrared. So of course that's what the alien will see, right? That will be Peter, I guess. Okay, so then in the movie, what he does, he cover himself with mud. Okay, so the infrared will not be produced, right? To block the infrared so he will go invisible for the predator, for the alien. Is that interesting? I guess they took physics, right? So you can use that also for space. So if you have a Hubble Space Telescope using visible light, you cannot peek through a nebula. So nebula is a cloud of dust and gas. You cannot peek through. But if you use infrared, okay, so a special kind of telescope to detect infrared, infrared does not care about dust and gas. It will just go through, like they don't see bend around, and you will see, you can peek through, you can see the stars hidden inside that cloud. Huh? Isn't that nice? So you need a visible vision and infrared vision, and you have telescope for gamma rays, you have telescope for X-rays, and then you combine all the images. So it used to be Spitzer was a telescope, infrared telescope, but it has been phased out. It's retired because if you have an infrared sensor, you need to cool it down. Otherwise, you're going to pick up anything around, all the pollution. And the coolant leaked out. I think that's what happened. Greenhouse effect. Okay, so you all heard about greenhouse gases. So the idea is the following. What's the physics behind it? Lucky for us, we have an atmosphere. Okay, so keep us warm, about 15 degrees Celsius average. Otherwise, life will not have been able to evolve on Earth. Okay, we need it cannot be too cold. Okay, like on Mars, for example, it doesn't have enough atmosphere even to keep the water liquid. So we have the right temperature on Earth. And the way it works is that the Earth is going to absorb radiation from the sun, including visible light and UV, okay? And it's going to re-emit infrared. So some of the energy from those radiations here, remember radiation is like energy flowing. Some of the energy will be going into heating the water, heating the ground, and then you have some infrared being burnt out. Some of the infrared will escape to space, but thanks, and it's a benediction, thanks to those greenhouse gases, okay, some of the infrared will be trapped. So it's behaving like a blanket, okay, keep us warm. So greenhouse gas are very good. So people think that you have to blame for CO2 and you have to blame the cows and you have to kill all the cows. But what most people don't know is you have something most more dangerous than CO2 with a 20 times more effective as trapping heat, and that will be that component here. Okay, I'm not sure if I'm going to try to say it. Sulfur hexafluoride, fluoride, sulfur hexafluoride. Hexa means what? Six?
Six.
Ah, okay. Sulfur. So one sulfur and six. See, you are good in with chemistry, right? Exactly. So very, very bad. And they never talk about this chemical because, of course, it's used a lot by big chemical plants. It's used for electrical equipment, insulation. It's used in semiconductor manufacturing, and you have semiconductors, everywhere in electronics and MRI. So, zip it, quiet, don't talk about it. Just talk about the CO2 and the cows. And then I'm just kidding. So nitrous, another one that is also very potent, 300 times more potent than CO2. It's so do I say it right? Nitrous oxide. Okay, nitrous oxide, and it's used as fertilizers. Also greenhouse gas, more potent than CO2. So I don't know why they don't like cows. Aren't they cute here? So this and that one are really the bad guys. Okay, so other applications, infrared, um, snakes. Then that's how they find their prey. Okay, through the heat. So they're gonna see a mouse, even if they don't see the mouse invisible with the visible light, they're gonna see it using infrared. So they feel the heat. So a mouse can try to hide, but it's not going to work, right? Because it's always emitting heat. In the military domain, you have something called stingers, and stingers are special kind of missiles with infrared sensors. Okay, so infrared sensors are sensors that will feel the heat. So, for example, when you have an airplane or a tank, okay, you shoot your missile. Not that you want to shoot missiles, just to give you an example of applications. The missile will right. It will track the heat, okay, and it will follow that. So it's called stingers. That story here is from the book. I was telling you what happened here. There were stingers. It was at the time when Taliban were the US friends. So the US, oh, because it was, I remember, it was the Cold War. So it was between the US and the Soviet Union. And the Soviet Union were in Afghanistan, and the Taliban were fighting what? The Soviet Union. That's what happened. So the US gave the Taliban stingers, and on the black market, it ended up in Rwanda. And one of those stingers shot the plane of the president back then, and it started the genocide. So the story is like a little butterfly, um, flapping its wing in one place can make like a hurricane at another place. Well, that's from the book. Anyway, mosquitoes also use infrared. Okay, so you can hide as much as you want under the blanket. Um, they will get you. Horrible. I hate mosquitoes. Other application here, thermometer. So in France, when I was a kid, okay, we didn't have that. Okay, we have a different way to measure temperature that I don't want to go into details. But when I moved here, I discovered this. That's very convenient. So you see, it's using heat infrared. Okay, so you put that in your ear. You have infrared radiation, and remember the type of infrared, the radiation, the wavelength depends on the temperature. Okay, so there is a direct relationship between the temperature and the type of radiation. This is called black body emission. Okay, so that's another way to use. Okay, any question? I hope it's not too much. Guys, you see, it's relaxing, no math today, just conceptual questions. Another, so we did gamma ray, X-ray, UV. Okay, a question on the final. You need to know the order, right? Gamma ray, X-ray, UV, visible light, infrared, microwave. So microwave, the size of a microwave, it's not micro. Okay, it's more like centimeters. Okay, so 1, 2, 3, 30 centimeters. In that case, 3 centimeters. So from 3 centimeters to 30 centimeters, that will be microwaves. Okay, application microwave oven. So if you have food, and the food has to contain water, otherwise it doesn't work, right? And you have microwaves here. And remember, an electromagnetic spectrum is made of an oscillating electric field that will induce an oscillating magnetic field, that will induce an oscillating electric field, that will induce an oscillating, I forgot. I don't know where I am, but you get the idea. Okay, so you're gonna have an oscillating electric field inside, you see, and because the water molecule, as you all know, because you are all um, very good at chemistry, the water molecules are polarized. Very good, polar. It's a polar molecule, exactly. So you have a plus here and a minus here. So the electric field is going to shake it, right? The plus here wants to go the electric field, the minus wants to go against it, and all of a sudden the electric field flip, oh, change of direction, right? So it's going to do something like this. Okay, it's going to twist, twist, twist the twist. And that each time there is a motion, there is a heating. Okay, so all that kinetic energy goes into heating the food. So that's why if you have a pie, for example, inside the microwave, the crust will stay cool. So you go for it, bite it, and ow, you burn yourself because the inside of the pie is liquidy. It's like a liquid fluidy. Um, it's liquid, so it's gonna be hotter. Right? Any question? Okay, so the radar. So we talked about the radar also used to bounce off airplanes. Yes.
Could you repeat the order that you said the rays and like gamma rays?
So gamma rays, the bad. You think bad and good. Bad gamma rays. Then X-rays still bad, but not that much. And then UV still bad, but not that much. And then visible light. And then you have visible light, you think that you have blue to red. So next to red, you're going to have infrared, because you have the word red, infrared. And then microwave, because they are tiny radio wave. So they are microwave, centimeters long. And then you have radio waves. So you can use microwave. So that was developed during World War II by the British to bounce off an airplane. Okay, so all waves go at the same speed of light. You can find the time it takes to bounce off, so you can find the distance. So that's used, for example, by bats. Bats, no. Do they use microwave? No. No, they use ultrasound. Ultrasound, right? Echolocation. Do they use I think they use sound, ultra sound wave. Okay, so that's not that's just to give you the idea of echolocation. Thank you for the word echolocation. Okay, so it's the same idea, it's bouncing off. So now if you have in the military, they have developed a technique called stealth technology, because they don't want to be seen by radar. So they will make their plane very weird looking with sharp angle like that. So that way the wave doesn't bounce and go in the same direction. It will bounce off, but in a different direction. So basically the airplane is invisible to the radar. So that's why when you see those very weird military airplane, they have this very weird angular shape. So this is called stealth technology. Same thing here. You have a submarine. You don't want it to be seen by radar. You make it very weird looking. It's called stealth technology. Okay. And then you have another technology where you can use microwave also as a way to imaging. Okay, so it means it's advanced technology, but basically the waves will bounce off the target, and you get an image like this. So this one will be the Pentagon, I guess. It's called SAR. Okay, so that's a funny story. I found it funny. So it used to be, okay, I have the date, 2010. See this? Okay, in 2010, okay, what happened in 2010? There was a tentative of bombing an airplane. So in 2010, they they brought X-ray scanners in the airport. Okay, before boarding a plane, you will have to go through X-ray scanners. But those X-ray scanners, as you can see, they were very revealing. So there was a whole discussions about that. Maybe it was distracting the security agent a little bit too much. So that was in 2010. So in 2012, 2013, they introduced a new technology, and they use radio waves, but very small radio waves, right? Still to see the details. And so they use what it's called millimeter wave scanner, millimeter wave. Okay, so that way it's not too much revealing, but you can see if someone has a gun or whatever. It costs a lot of money. $150,000 per unit. So it's called a full body millimeter wave scanner. And so it didn't last long. From 2010, X-ray back scatter X-ray scanners, the one I was telling you about, at the beginning. So it means X-ray bounce off, a little bit too revealing, and they spent $40 million just to replace them 2 years after. Isn't that crazy? Huh? What could we do with $40 million? We could buy a lot of Van Graph generator. Okay, that's my dream. Okay, I have a nice Van Graph generator so I can have all those demos. Another application here, if you want to see the endoscopy, to see what's going on inside, you can have the patient swallow that, and it used to be that you have to retrieve it in the stool, but not anymore. There is a different way you can send the information through radio waves, right? And there is a detector outside, so you can go through the stomach, intestine, and intestine. Okay, today I'm very tired. So also interesting. And then we get to radio waves. What do you say? We start the pop quiz now and we finish that next time. So I